I had intended to actually make a demo that was designed around an elevator that was tied in with the mechatronics course. And I wanted it to be simple. I wanted it to be kind of like an exploded view of the inner workings. And I came up with this idea. This idea is based around something that I love, which is cutting boards. I love cutting boards. Cutting boards are readily available, easily machinable, flat, sometimes have a texture, sometimes do not, sometimes are very smooth, typically have a built-in handle for carrying from place to place, and allow you to make devices and prototype projects very, very quickly. And I was going to make an elevator demo that incorporated an Arduino with a motor control running on a pulse width modulation output, an optical triangulation based distance sensor watching a piece of plexiglass with 4 bearings running in tracks made of DIN rail. DIN rail is another one of those wonderful quick prototyping materials. They come in a very standard shape. They're very inexpensive. Once you have it positioned on your project, if you need to modify the position slightly, they come with the slots built in. They're lightweight. And the bearings that I had were actually, they had a pulley-like U-shaped profile, which would have fit this perfectly. I don't unfortunately have those bearings anymore, but I'll probably end up using something like that. The elevator was not simply going to be a winch, but it was going to be an upper pulley running with a gear motor with some sort of limited slip device, probably a magnetic clutch, so that if it got into trouble and tried to pull itself apart, it wouldn't be able to. And like real elevators, which have counterweights running in the shaft with the elevator, I was going to make the counterweight heavier than the elevator, because the counterweight in an elevator is typically designed to be more than the elevator, so that when an elevator is partially loaded, it's perfectly balanced. And when it's lightly loaded or heavily loaded, those two maximums are not that different. Now, I don't know for a fact whether my final project is going to be something like this, but I do know that I want my elevator to be PID controlled. I want it to have a position feedback and have the motor that's driving it be running through a PID loop to do the positioning, do the velocity control. I'm going to make this project in multiple videos, and I'm actually going to make the first module be an intuitive creation from scratch of a PID loop controller implemented in Arduino. Now, you may or may not have ever seen one of these, but what it is a 10K motorized potentiometer. These are used in control systems, especially places like audio engineering labs, where a person wants to be able to physically move a control with their fingers. But they also want to be able to quickly save and recall presets for setups that have worked before. These audio engineering labs can have dozens or hundreds of different controls, all of which need to be individually set. Well, the easiest way to set it is to have feedback from a potentiometer for the position and a DC motor running a belt drive. So this right here is a linear actuator. It doesn't have any intelligence at all, but what it does have is the ability for me to connect 5 volts and 0 volts to 2 of these terminals, connect the third terminal to the Arduino's input, the analog input, and get a 0 to 5 volt feedback telling me where the control is. I can push that through the PID loop and have the PID loop tell me what to do with the motor and have the motor drive this. I'm also going to take advantage of the fact that I have 3 of these. And this one is going to be an actuator. This one is just going to be the set point control. So I'm going to use this one on one analog input to tell this one where to go. Now, I didn't buy these recently. I picked them up at an electronics surplus store in Toronto. And I can't find the datasheet online for them. B10K-10V basically tells me everything that I need to know. The potentiometer itself has a full scale, a full length resistance of 10 kilo ohms, and the 10V would be the maximum voltage that the motor can take. I don't necessarily need to drive it at 10 volts. And I would like to know a few things up front. I would like to know what the polarity is versus the direction of travel, and I would like to know which terminals on the resistor give me a proper feedback. Now, proper feedback is subjective, but in my case, I'm going to take the motor side to be essentially 0. This will be, 0 ohms or 0 volts or down or backwards, where this will be forwards or up and an increasing voltage from the feedback. So if I set this at, say, 25%, roughly, of its total travel, and I check the resistance of the 3 terminals, what I should find is from one terminal to a second terminal, I will get the full resistance of 10K. So the terminals are T1, G, 2, 3. This is 2, this is 3, this is 1. 1, 2, and 3 would be the potentiometer. G is apparently connected to the metal housing for shielding purposes. And T is touch, which is quite a neat thing. You not only do you have the motor that can drive the potentiometer back and forth, not only do you have the position feedback from the internal resistance, but if you can detect capacitive touch with the input of the microcontroller that you're using, then you can detect whether or not a person's fingers are on the control. For the moment, we're not using that. For the moment, I want to just verify that terminals from 1 to 3 should be 10,000 ohms. Give or take some percentage tolerance. So in this case, this unit is 9.9K. Now, with the control closer to the motor at about a 25% position, I want to know which terminal is closest to the wiper. So with the 10K pot, I would expect about 2.5K between terminal 2 and either terminal 1 or 3. So let's just go with terminal 2 and terminal 1 to start. .2. So a little less than a quarter. And if I move this over to the other end, I should get the other proportional 7.75K. So what this tells me is that if I want this to be my 0 position, and therefore the minimum voltage going to the microcontroller's analog input, I want to detect the voltage at pin 2 with respect to ground connected to pin 1. And that leaves 5 volts from the Arduino to be connected to pin 3. The second question is the motor. So if I take a resistance reading of the motor, 16.4 ohms. So with the resistance across the DC motor's terminals being 16.4 ohms, we can calculate that the current at 10 volts would be 10 over 16.4. And finally, if I want to move the slider to the right in the increasing direction, since we've decided that the resistance-based feedback, the voltage feedback, is going to be increasing to the right, I'd like the motion to increase to the right as well. The question is, do we put the positive here and the negative there, or the positive there and the negative there? And that is easy enough to find out by connecting the power supply. So if we connect the positive to that terminal and the negative to this terminal, start off at 0 volts, limit the current to 1/2 amp, and increasing the voltage by 1/10 of a volt at a time until we get some minimum voltage required to drive some minimum current through the motor to generate some minimum torque in the motor that will overcome the small resistance, the friction in the system. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1 volt. And at 1 volt, we're drawing 60 milliamps. 1.1, 1.2, 3, 4, and I see a little motion at 1.4, but it barely moved. 1.5, 1.6, a little bit more motion. 1.7, 1.8, 1.9, 2, 2.1, 2.2, 2.3, and with a lot of effort, 2.3 volts was enough to have this drive all the way to the end. So the minimum voltage required for this motor to actually move is 2.4 volts and 143 milliamps locked rotor torque. Now I'm going to be nice to the motor and I'm going to turn it off for the moment. We're going to reset and I'm going to bump it up to 3 volts because now I want to know what voltage I need to get a reasonable rate and consistency of motion. So at 3 volts it does this. Not bad. At 4 volts, that's pretty zippy already. So if we consider the maximum to be 5 volts for our initial testing, that's pretty zippy. And at 5 volts, we're at 295 milliamps. So at 10 volts, it would be about 0.6. Okay, so we've got our cutting board, and I've got the DIN rail cut to length. At one point, I thought about mounting them along the cutting board like this to give more space for the electronics and sensors and buttons, but realistically, that didn't leave a lot of room for actual motion. If I used this plastic project box, which has no other function in my basement other than taking up space, and used as part of an elevator project, it's kind of cool because you can put things in it to change the mass, and you can see everything beside it and around it and above it and behind it to make it a very cool, visible project. Problem is that it takes up a lot of space, and originally, and I had found this decorative box that I picked up from Michael's before the pandemic as a housing for an Arduino Mega for my crawler project, which is, I think, kind of cool retro elevator like, and you can also see inside it. And the Arduino with the motor shield mounted on it has plenty of space, but I'm going to actually flip this, and I'm going to have the rails mounted long ways, lengthwise, to maximize the available linear motion in our project. As much as I like the clear box, it takes up a lot of space, so I will probably end up just
swapping it out for a hunk of metal. So where does all that leave us? That leaves us with this, which is not 100% complete, but it's as complete as I'm going to make it for now. Specifically, I have decided to not integrate the motor from scratch just yet, because it's initially going to be just an indicator. I'm not going to have it acting on anything, and for the time being, it would just complicate things. Not very much, but it would complicate things. So the physical construction of this elevator demo is as such. We have the cutting board, we have the DIN rails, we have the carriages. This is going to be the elevator, this is going to be the counterweight. The counterweight has spiral notebook springs to maintain tension on the paracord elevator cable. We have a DC motor with a belt reduction drive driving the paracord elevator. I have an Adafruit Motor Shield V2, which can control essentially 4 bidirectional channels of up to 1.5 amps each. I have left these 2 channels to drive this motor later. These 2 channels, M4 is connected to the motor of motor pot 1. Motor pot 1 can be driven by the motor shield, but largely is going to be feedback for the elevator position. This motor pot is not initially going to be driven, although it could be used for interesting things like force feedback. For now, we're not driving it. It's just going to be an input. And for now, it's going to be an input to the PID as a set point. The NeoPixel strip is 12 LEDs long. NeoPixel 0 is up here, NeoPixel 11 is down here. And I'm not sure what I'm going to do with the top 4, but the top 5, I should say. But I do like how I very neatly spaced 7 NeoPixels along the length of the motor pot, because we can have a 0 position and then a plus 1/3, plus 2/3, plus 3/3, minus 1/3, minus 2/3, minus 3/3 position. At the moment, the code that I'm running is mystery code that I will actually walk you through in the final video. But for the moment, what I have is an array running on the Arduino with the green LED being controlled by the set point. The blue LED being controlled by the process value, the feedback. And the red signifies the control value output, which on the middle pixel means 0 output. Alternatively to the analog position feedback, I have added, instead of physical tactile push buttons that go on the breadboard, I've chosen to use this nice little capacitive touch input board, which also takes away the necessity for pull-up resistors and pull-down resistors. If I touch it, I have code in the Arduino that ignores the motor pot position. So right now we're going to floor 1, floor 2, floor 3, floor 4, and if I release it, it goes back to wherever the motor pot is. The motor pots can handle up to 10 volts, and the DC motor didn't work very well on 5 volts, so I removed the motor jumper that took power from the Arduino board and am now separately powering it by the DC power supply that's over on my desk over yonder. So I'm supplying 10 volts to the motor shield, which will give me 10 volts to the motor pot, making it much more nimble and making this work at all. Now in the next video, the very first thing that we're going to do is play with the PID and get it reasonably well tuned. The initial PID is going to be controlling the motor pot directly. So the feedback is, of course, driven by the motor pot. But then when we drive the elevator, that's where this comes in, which is a nice little yoke, which fits over the carriage and fits over the feedback position and screws in. Let's have some fun.